Welcome to Chemistry 111. Today we'll go ahead and continue talking about thermodynamics. As I said, this starts to get a little bit math heavy as we go forward. If you are ever confused, feel free to reach out to me, come get help. It is not supposed to be particularly, I don't want this to be super challenging. I don't want test number 3. So if you're ever struggling on a ton, reach out to me, whether it's by email, you want to make a special Google Meet after this so we can talk. I don't care. In person, whatever. Let's just sort this out. You can come get your test after the class or sometime this week. I will post a video going through the test before you know it. Though I spoke incorrectly to a student earlier. Someone had asked, will there be extra credit opportunities? And in fact, yes, I just remembered there was something I needed some help with. Near the end of the semester, after we're done with all of our proper labs, I know the other chemistry professor and I need to fully rearrange the science labs before the start of the summer. And so you might need help taking glassware out, cleaning it, checking it for cracks, help rearranging stuff so that we can put things back in some semblance of order rather than the kind of drunken stupor that it seems to be in right now. So that will be available probably further on in the semester. Not quite yet because we're still doing some labs, but soonish. So there will be that opportunity coming up. In the meantime, as I said, test number 3 was not super good, but I gave a pretty generous curve. So with that in mind, we'll go ahead and get started, continuing talking about thermodynamics. We'll start with our PowerPoint. So quick reminder, we introduced the concept of internal energy and the idea that the sign of energy matters because we're talking about systems, surroundings, and the first law of thermodynamics states that energy has to come from somewhere, has to go from somewhere. So when we burn a fire, the heat that the fire produces comes from the destruction of the chemical bonds in the wood. We're oxidizing those bonds to turn the carbon and the hydrogen into CO2 and water, and that is releasing the heat. So when we look at the change in internal energy of the system, we can measure that typically as heat flow and the work flux on the system. Yes, there will be kinetic energy, potential energy, electrical energy, but for the most part, when it comes to chemistry, we will focus largely on heat and work because unless we are doing oxidation reduction, we're not going to see any electrical chemistry. And since the molecules are so small, oftentimes we're not going to see much of a kinetic energy. So we're going to look at it as the energy of heat flow and work that comes from gases expanding. Now, the easiest thing to do is simply to determine the internal energy change in a system by a word problem such as this. The only trick here is trying to put the correct signs on the work based on the verbiage. The idea that if heat goes into a system, it is positive. If heat leaves a system, it is negative. If work is done on a system, thus goes into the system, it is positive. If work leaves a system, is produced by the system, it is negative. So a particular engine absorbs 58 joules of heat and then produces 70 joules of work. What would the internal energy of that system be? So simply put, you have Q of positive 58 because it absorbs. The engine absorbs the heat, but the engine produces 70 joules of work. So delta U is just going to be, in this case, Q plus W. So Q plus negative 58 plus negative 70. The net change would be negative, like 12 joules of the internal energy change as it does that. Green. Okay. So that one by itself should not be super tricky. However, don't be lulled into a false sense of security. That is the absolute easiest thing we can do. It does, it gets harder from here. But don't be confused if I throw at least one of these problems on a test. Don't look a gift horse in the mouth. This should be an easy one as long as you can figure out, oh, it produces heat. Oh, that would be a negative Q. Oh, work goes into it. Oh, that would be a positive W. So one of the concepts here in this chapter and in some future chapters is the idea of a state function. Internal energy U is a state function. A state function is kind of hard to understand until we really get into some examples of this. But a state function is defined by when we define a state function, it will have a capital letter. So whenever we see a unit that has a capital letter, typically it is a state function. There are some state variables such as pressure and volume and temperature. Those are often given as capital P, capital V, capital T. Or our internal energy is capital U. Any letter that typically doesn't have a capital letter is a non-state function. But what is a state function? A state function is a function calculating some path-dependent system, but the idea is that the path itself does not matter. The path itself does not matter when calculating this. So I could go about this calculating any number of ways, and the net answer will be the same. That it only matters on the initial states and the final state. Some things you can measure are path dependent and some things are path independent. If I were to fly around the world, go to, I don't know, like Russia, depending on whether I went east or west around the globe, there would be a different distance traveled. There would be a different time of flight. But all in all, the net distance between me and Russia right now is the same. Because my location and where I'm at right now are never going to change. The distance traveled to get there will be different. But right now, the absolute relative location between myself and my destination will not change because neither of us will be moving. Or at least we'll be moving as the Earth rotates relative to each other. The whole idea here is that if I know the initial starting point and I know the final starting point, I can calculate this without caring what scenario this is in. It doesn't matter what combination of work and heat we calculate for. Internal energy U should be the same. You could imagine a scenario where the work goes up and the heat goes down, or the heat goes up and the work goes down, but the change in internal energy will be the same. So hypothetically, when I combust an object, I'm losing so much energy. I'm losing a set amount of energy. Now, that set amount of energy will not change because we have a starting value of what energy is stored in there and a final value of what energy is stored in our CO2 and water. So because the internal energy when I burn one log is always going to be the same, the idea being, if I want the maximum amount of work, I would have to minimize the production of heat. If I want the maximum amount of heat, I would have to minimize any work produced. And that in automobiles, for this same concept, heat loss is a big efficiency drain. Most engines only work at maybe 30% efficiency at highest, meaning that they produce a lot of heat that comes out on the tailpipe. We produce the gases that expand and like move the engine, but a lot of it goes out as a heat loss. And so we're losing a lot of the energy we get from the burning because we do not have a more efficient engine. But the idea here is we can calculate something more than one way and get the same value because of its state functionality. Now, we're going to introduce delta U and delta H in this chapter. But next semester, God willing, we're going to have delta G and delta S. The Gibbs free energy and entropy, all this is our state functions. We also might even look at electrochemistry, the E cell, which is capital E, which is going to be a state function as well. The whole idea here is, I'm going to go to DocCam because we're going to see this problem later on. We're going to see the problem later on. But one of the ideas we're going to get is, if I know A goes to B, and I know B goes to C, I can calculate A goes to C by adding these two together. Oh, thank you. I can, if A goes to B and B goes to C, I can calculate A goes to C by adding these two steps together, because the state function does not care how many intermediate steps are in between. The idea is that our starting point is A, our ending point is C. We can go through as many steps as we need to in the meantime, because we're just calculating from the starting and ending point. That's one of the ideas of a state function. If I know this and I know this, I can calculate this. And in fact, that's how they go about a lot of the calculations in here. Some stuff, it's really hard to find out what this number is. But how can I find it? I can find it through various intermediate values, going about a roundabout way to get to where we need to be. But the state function is kind of a head scratcher at first until we really start to see it. So, but this is a big thing that we will see this chapter. So the first major, we've introduced internal energy, but internal energy doesn't get used very often. The notion that is the workhorse of this chapter is enthalpy. Maybe you've heard of the term enthalpy, maybe you have not. Enthalpy is the state function version of heat. It is the heat exchange defined at a constant pressure. That's the actual definition that we've predefined. The easiest way to measure this as delta H is heat exchange when you're allowing pressure to remain constant. In terms of everyone around us, constant pressure would be like atmospheric conditions, we're allowing a gas to expand and contract under a constant external pressure, which is where we're at. So it means we do an experiment in a beaker on the bench top. We're not doing the experiment in a closed, sealed container. We're not hermetically sealing it in a bubble and then reacting. We're allowing it to react right here, right now. This is how most chemistry is done, and that's why enthalpy is a very useful thing, because it's a state function version of heat that's done under normal situations. Now, if we consider the work done under a constant pressure, now we haven't introduced really pressure yet, because the gas chapter is next chapter. But pressure is defined as a force applied over an area. So if I have a force of my hand pushing down on the desk, the force applied over the area of my hand, the surface area of my hand, would be the pressure I'm exerting on this desk. In terms of gases, it's the force of the gases ricocheting against the surface of, say, the container. And if volume is defined as the area times the distance, so length times width times height, the distance being the height component, we can say that pressure times volume would be a force times the distance. And force times distance is also work. So essentially, we can say that work at a constant pressure is defined as negative P delta V. That we're looking at this, the negative sign allows it to have the correct units. The idea being, if a gas expands, it does work. If a gas expands, the volume goes up. So how do you have work leaving the system? You have to make that negative. But so we've rearranged our equation. Instead of delta U equals QW, we can say delta U equals delta H minus P delta V, as a specific thing of calculating this at a constant pressure. Now, what is an explosion? Explosion, by definition, is a gratuitous amount of heat gets produced and gases rapidly expand under a constant external pressure. I mean, a grenade. How does a grenade work? You have some sort of igniter, some sort of explosive in there. You have a constant shell. You have like a hard outer body shell. The gases explode, produces a bunch of heat, causes gases to expand rapidly. The shell cracks, fragments, shooting the things everywhere. Especially in fragmentation grenades or things like claymores. It's not so much the explosion that hurts you, it's whatever the objects it shoots out when the gases expand that does all the damage. Little ball bearings or nails or whatever horrible things are in there, all created by the expansion of gas, this pressure that forces them out. Even our car is a controlled explosion. We're putting fuel in there, some oxygen, we're igniting it. Small explosion pushes piston up, and we get some energy. So now, one thing we have to worry about is units. That if enthalpy is in kilojoules and we want to add the work into that, we need kilojoules. Joules adds to joules, kilojoules adds to kilojoules. We cannot directly add a liter atmosphere into a kilojoule because the units are dissimilar. Just the same way as we can't add an inch to a centimeter without having some major confusion. You have to convert first. So this problem here, What would the internal energy be for a system that absorbs 123 kilojoules of heat and is allowed to expand by a volume of 58.94 liters under a constant external pressure of 3 atmospheres? So writing down all that we know. I'm always going to try to define what we know, because that's going to help us when we actually try to do the problem. Be able to look at this. So we have our H. Now we have to get this term, our work term. Our work term, negative P, 3 atmospheres, times 58.94 liters would give me a unit of liters per atmosphere. See, I forgot my calculator, so we'll do it on my phone. So 3 times 58.94 is negative 176.82. That's liters per atmosphere. However, we have to turn this into joules. So negative 176.82 liter atmospheres. I'm going to put liter atmospheres on bottom to cancel with liter atmospheres on top. So I multiply by 101.3 joules. However, there is 1,000 joules in 1 kilojoule. I'm going to go ahead and convert this all the way to kilojoules so I can add kilojoules to kilojoules. So times 101.3 and divided by 1,000. So I get negative 17.9 kilojoules. Now, plugging this back in, we have our 123 and negative 17.9. So a net effect of 105.1 kilojoules. That's the internal energy change for this system, 105.1. Now, one thing we'll have to watch out for is units. Units aren't supposed to be super hard, but we got to watch out for our units before we do any addition or subtraction. Okay. Now, one of the major concepts we'll talk about, and if we do this lab, I think we might be canceling this lab because it's like one of the last labs and we lost a week due to the snow, but deals with specific heat. Specific heat is the idea that how heat flow affects an object. We're going to talk about calorimetry, which is a study of heat flow in reference to various objects. Now, specific heat is a constant for every material. It's specific for every material. And so if you can figure out the specific heat, you can actually find out the identity of an unknown by calculating how well it heated up or cooled down with reference to its density. Every object, will absorb X amount of heat and release different amounts of energy in relation to their temperature. Metal, as we all know, is very easy to heat up, which is why we use metal cookware. Not just because it has a high melting point, but also because it takes very low energy to heat up. Otherwise, would cost a lot of energy to do that. Organic liquids and water are rather difficult to heat up. If you've ever tried to boil water, it takes a lot of time because you have to pump a lot of BTUs of heat to change the temperature. Now, the specific heat capacity which is the unit capital C, is defined as the joules of temperature needed to warm 1 gram of an object by either 1 degree Kelvin or 1 degree C. Now, you'll notice C or K used interchangeably, because the idea, if I add 273 or not, it won't matter because we're looking at a change in temperature. So both numbers get added 273 or not. So the 273 will cancel out. There's oftentimes also used as a molar heat capacity, which looks at instead of grams of object, but moles of object. But more often than not, we will use a specific heat capacity, which is just joules per gram. So you'll notice the unit down here, joules per gram K or joules per gram C is to match what we have here. Now, how this is used, we can look at this as the heat flow. So Q, heat flow is the mass times the specific heat times your delta T. This is often given as the equation Q equals mcat. The delta sign looks like an A, but the idea is mass times your change in temperature times your specific heat all gives us energy in joules. And if we watch our units, joules per grams Kelvin would multiply by grams, multiply by Kelvin to give us just joules. Watching our units cancel out to give us just joules when we're talking about heat capacity and our heat flow. Now, to use this, we are going to oftentimes either be solving for the heat or solving for the specific heat C, or maybe even solving for the mass, but we're just rearranging certain equations. Okay, I'm going to write some of these numbers down. Quick, C of water, 4.184. Density, 1 gram. C of 10, 0.22. So how much energy would it take for 4 liters from 25 to 100? And then 5 kilograms from 25 to 170. So I just want to compare tin to water, just to show you what it means to have the difference between energy to heat up water, that energy to heat up a piece of tin. So we're in both these cases, we're solving for Q. Q equals mc delta T. So if 4 liters of water, what is the mass? The density of water. So 4 liters times, there's 1,000 milliliters in 1 liter, and in 1 milliliter, there's 1 gram. So the amount of water should be 4,000 grams. Okay. Temperature, our delta T, is going to be 100 minus 25. However, what if I did in Kelvin? Hypothetically, what if I did in Kelvin? I'd have 373 minus 298. You do this math, this is 75, this is 75. It doesn't matter whether they're in Celsius or Kelvin, they will give you the same answer. Fahrenheit, well, Fahrenheit, you're screwed, but we're not doing Fahrenheit. And specific heat of water is 4.184. So, looking at here, 4,000 times 4.184 gram Celsius, grams, times 75 degrees C. C, grams, grams. What's our number for water? 4,000 times 4.184 times 75. It's going to be a really big number. It would be in joules, 1,255,200 joules. Or if I turn this into kilojoules, 1,255 kilojoules. Okay. Looking at the tin. Q equals mc delta T. The C was 0.22 joules per gram C. The delta T, we went from 25 to 170, so that means it's gone up by 145 degrees. And the mass is 5 kilograms, which if there is 1,000 grams in 1 kilogram, that would be 5,000 grams. So if you'll note, the weight is higher, the temperature is higher. But what we'll see is the heat required is much, much lower. 75. This only has 82,500 joules. 82,500 joules. Comparing that to the 1,255,200, that number is something like 15 times less. Even though tin required had 1,000 more grams and had almost double the temperature needed to go up. That's 15 times less heat needed. That's because the heat capacity of tin was so low compared to the heat capacity of water. But simply put, I define my mass, my heat capacity, and my temperature change, and I can find what heat is lost or gained. Let's see. Something screwed up there. 170 minus 25. 0.22 times. Oh, shoot. Bad math. I multiplied by 75 down there. That would be it. So, okay. That should be 159,500. I multiplied by 75 degrees instead of 145 degrees. But even so, the whole idea here is it would be so much less energy to heat these up. Okay. Now, how do we measure calorimetry? How do we go about measuring calorimetry in the real world? How would we do it if we were to do this in lab, which we may not be doing in lab anymore because of, well, losing a week? Now, to measure a compound or a reaction, we would use something called a bomb calorimeter, or as one way to do it. And there's various different types of calorimeters, but it uses the basic concept that heat is conserved. We will probably have problems involving calorimeters. It uses the idea that heat is conserved, that the heat flow in the universe is essentially zero. So if I add the heat of solution to the heat of the surroundings, the net heat change will be 0. So this is actually going to use the idea that the heat of a reaction is the inverse of the heat of the solution. The heat that a reaction will produce will equal the inverse of the heat absorbed by the liquid around it. So the idea here, we can't measure the heat of the actual reaction, but you can measure the heat of everything around it. When I put a solid into water and it dissolves, I'm not measuring the heat of dissolution, I'm measuring the heat flow of the water itself. How much does the water get colder or hotter when I dissolve this? And by measuring the temperature that the water changes, I'm going to figure out how much heat the solution either generated or absorbed. If you come by this and see the student members of the American Chemical Society, we've done some demos called fast freezing, where I pour a salt into water, stir it real well, and have a beaker freeze onto a block of wood. It absorbs so much heat that the water itself will get down to below freezing, and it will absorb heat from the water outside of the beaker and freeze it onto a block of wood. Now, what we will do is we'll measure the temperature of the surrounding solution, and from that we can know the idea of how the heat is flown. Now, it doesn't matter whether we're looking at the QP or QV or whatever, or Q equals MCAT. The whole idea is that if I measure the heat of the system and the surroundings, they will be 0. As I said, there's two major types of calorimeters. A calorimeter is defined as a thermally insulated reaction vessel that can either be held at a constant pressure or a constant volume. So a constant pressure one is just what we would have done in lab, is we'd put these coffee cups together. We would, to try to thermally insulate them, use some aluminum foil, but allowed it to react open to the air. Now, a constant pressure one essentially seals it up. A constant volume one seals it up, a bomb calorimeter. It's an enclosed vessel that insulates the reaction using a layer of water. We then combust the sample in there, and we measure the water temperature around it. But we can use a calorimeter to figure out whether the specific heat capacity of an unknown solid, or we can measure the delta H of a reaction or delta U of a reaction. So typically, if you're trying, a bomb calorimeter can be used to find how many calories are present in a certain food. If you got a food with a calorie count, it probably went through some sort of bomb calorimetry. They burned it up, seen how much energy it generated when I burned this up, and measure that in the terms of water warming up. By doing that, I'm able to say, well, if burning this gave me this much energy, your body would get that much energy when it consumed it. So they're able to figure out calorie count through bomb calorimetry. Now, so when you're calculating the C of the unknown, you're using the two situations. You're essentially saying, let me just show this real quick. So there's a lot of crazy math here that I like to just jump in before I go too far. The idea here is we're setting two scenarios up and equal. Q of water equals Q of unknown. Q of water equals negative Q unknown. So Q of water is going to be M of water times C of water times delta T of water. Q of unknown is going to be mass of unknown times C of unknown times your delta T of unknown. And basically what they're saying here is that if I'm solving for C, I know everything with an asterisk on it. I know everything with an asterisk on it before I even put this in there. I know those things. These would be with the double, I'm going to put it with a double dagger. Everything with a double dagger would be physically measured. The temperature of water, you would measure that. The temperature of the unknown, you would measure that. You would have an idea of what that is. You would put those in, and you could measure how they changed. And from that, we could find out what is the C. And the equation they have is they've rearranged this so that just the C is on one side. However, say we're making a reaction. We're saying Q of water equals delta H of reaction. So, but we have to account for how many moles are in there. So moles, N, letter N. We have to account for how many moles are in there because we're trying to figure out, we have to account for the total mass. But the same thing, it's be the mass of water, which is known, the C of water, which is known, the delta T of water, which will be physically measured, and the moles, which would be known. The idea is we're rearranging this to find for delta H. That's how it's done empirically. That is how it's done in the real world. You have a new substance. You generate the new fuel source and say, I want to prove this is more fuel efficient than gasoline. You get more bang for the buck. You put it in something like this, you burn it, and you can measure how much energy density this contains. Measure this in terms of energy density. And so they've just rearranged this to look at, to solve for the unknown. Now, one thing that would have come up had we had to do lab is we had to consider the heat capacity of the calorimeter. The calorimeter itself would have absorbed or released some heat. And we would have had to count for that. But okay, let's see what the next slide has to bring us, because we have 5 minutes left. We'll go ahead and try this one. Let's see if we can get it done. If the heat of 50 grams of iron balls, if we heat 50 grams of iron ball bearings up to 100 degrees, and then we drop them into 10 mils of water, 10 mils of water at room temperature. The final temperature of both are 21 degrees. What is the heat capacity of the iron, assuming no heat is lost to the calorimeter? So for this one, we're given that the heat capacity of water is 4.184. Okay. Now, here's one important thing to take away here, is that when I put one object into another object, they will get to the same temperature. If I put a hot object and a cold object together, the hot object will cool down and the cold object will warm up until they get to the same temperature. So when I put the iron into the water, the iron cools down to 51, the water heats up to 51. So from looking at this that reaction, we have the mass of water, 10 mils is the same as 10 grams. The heat capacity of water is 4.184, and our delta T is final minus initial. The other side of the equation, the mass of iron was 50 grams. We don't know our C, but we know our temperature is 5121 minus 100. Please note, this math will be negative, but this negative and this negative will cancel out. Otherwise, we will have a negative heat capacity. So doing this, 10, doing the left side first, 10 times 4.184 times 5121 minus 25. You get on the left 1096.6. On the right, 5121 minus 100 times negative 50 gives you 2,439.5 times C. So if we divide both sides by 2,439.5, 2,439.5, we will get our heat capacity. 1096.6 divided by 2,439.5. Our heat capacity of iron is 0.44, we'll say 0.450 joules per gram C. So that is our heat capacity. We set one side equal to the other side. We plugged in everything we knew, and we solved for our unknown. So that is that is what we're going to be able to do. That is maybe one of the trickier types of problems. There can be even trickier problems than that, but that is a rather tricky problem. We will continue with some of this and look at more of the enthalpy of reactions on Friday. In the meantime, I want to thank you for listening in. Reminder, there will be extra credit opportunities in the lab, and I'll talk to you guys on Friday.